Hi, I'm Doug Canfield, and we're here today to present our Vectra WB360 and some of the innovations for skin imaging. But I'd like to start by thanking the CVPR organizers, specifically Emre and Noel, for setting the meeting up and organizing the event. And we're certainly very happy to take part in it. Um, Joining me today, I have Brian D'Alessandro and Oleg Bisker, who will also be presenting some of the innovations around this 3D whole body imaging system. Um, the first question is why are we in a workshop speaking about AI, talking about a 3D whole body system? And it really is around the fundamental belief that dermoscopy is really important, but it's only as good as the lesions that you put it on. And if you can record most of the skin surface with a single capture, you've created a data set that then can be looked at. All lesions can be analyzed at a given time point. And more importantly, we can map the anatomy to the body, and we can track those lesions over time. And then with lesions being carefully tracked, you can actually look at change detection. So all these things will be presented in this workshop. So I'd like to hand this over now to Brian D'Alessandro, who's going to present the first component with lesion analysis and anatomy mapping.
So this is the Vectra WB360 system. It's designed as a tool for the clinician to do photo documentation, and it enhances their ability to do lesion assessment and tracking over time. So we have a complete hardware and software solution to manage this whole body capture. And the benefits are that it improves the standardization of the imaging process. It saves the clinician and the photographer time and effort. And because it's so quick, it increases the patient comfort and reduces their anxiety. So the actual system is made up of 92 DSLR cameras, 46 pods of 2 cameras each, and the total capture takes less than 3 milliseconds, which eliminates issues with patient movement. We also take multiple modalities. We take both a cross-polarized capture and a standard white light capture to compare. So this is a video of the actual captures process. The patient stands in the center, and just like that, the flashes fire, and that's it. It's done. We have the captures. So after all the images are captured, they're processed to stitch them together and create this very high resolution 3D body model with not just the high resolution skin texture, but also anatomically accurate geometry. And this is also not just good for lesion management, but also surface area measurements, circumference and linear measurements, volume measurements, things like that. So this example shows the white light and cross-polarized captures of the same subject side by side. The cross-polarized capture eliminates the surface reflection of light and really allows us to better see the pigmentation of the lesions. The subject also highlights use cases beyond just lesion analysis, like vitiligo, which we see here. But this system is also good for wounds, rashes, psoriasis, or any large condition which might be otherwise difficult to image with conventional 2D photography. But the primary use case that we'll be talking about today is for lesion analysis. So here's an example of one patient who has over 2,000 lesions all across his body. Now, it's incredibly difficult to manage that number. The clinician will be looking for the ugly duckling lesion, one that stands out from all the rest. How do you find it when you have all of these lesions throughout the body? Well, what we can do is to do an automatic detection and segmentation of all the lesions on the body. Here we're seeing only the lesions that are above 2 millimeter in longest diameter. We mark them with a triangle here. But even though they're identified this way, it's still very overwhelming unless the data is summarized. So that's what we do in this spiral diagram. We show all of the lesions together, show them side by side, and crop them so that you're just focused on the lesions. And this really helps reveal what might be the ugly duckling lesions, because now you're seeing them in context with one another, and the clinician can see which one stands out. So for each lesion, we also produce automatic measurements like size, longest diameter, shape, color, symmetry, irregularity, things like that. Also anatomic site. So these are all filterable, and you can use them to narrow down to more closely focus on what you might be looking for. So this is all calculated automatically with the 3D body model and the 2D data, so the measurements are calibrated and they're accurate. So here, for example, is a filter applied to narrow down to the lesions only above 5 millimeter in longest diameter. So it's a way the clinician can narrow down to what it might be relevant to them. And each of these lesions are linked to the 3D body model. So when you click on one in the spiral diagram, it'll show you exactly where it's located on the 3D body, so you can find it on the body and see more context of where it's located if needed. And vice versa, any lesion that you might click on in 3D will map to show you where it is in the spiral diagram and what its measurements are. So one of the things we need to do to make sure that the measurements are accurate for each of these lesions is to correct for the perspective distortion of them. Because the lesions are initially detected and segmented out of the source 2D images. Those are the ones with the highest quality and the highest resolution that we have. So when we crop something like this out, a circular lesion may actually appear elliptical because the camera is located at some angle relative to the skin. But since we know the 3D geometry and we know where each of the cameras are located, we can apply the calibration to it and then adjust the perspective of the lesion to make it appear as if it were captured perpendicular to the skin. And that is what we use to do the measurements like longest axis or shortest axis or area. So we can make sure that these measurements are very close to how they would be measured clinically. But how are lesions detected in the first place? We want to make sure that to the extent possible, we're only showing lesions to the clinician as opposed to things like skin folds or parts of clothing, nostrils, belly buttons, or shadowy regions within hair, things like that. So it comes down to a classification problem of lesions versus non-lesions. And this is well solved through an AI algorithm, a deep learning algorithm that was trained on hundreds of thousands of examples of lesions and non-lesions that were manually annotated. The whole process starts with an initial blob detection algorithm, which finds blobs of any sort, and then later the classifier is able to filter out which are lesions and non-lesions. It can do this quite accurately with a false negative rate of 0.7% and a false discovery rate of 4.8%. We're also able to go a step further, and this was done with a collaboration that we had with the University of Queensland to subclassify the lesions into nevi or non-nevi. So through the assistance of expert dermatologists at the University of Queensland, we can now start classifying what types of lesions there are. Doing the lesion analysis at a single time point is very useful for the clinician, but the benefit becomes even more profound when we start comparing the lesion analysis across time. So if there are several time points of 3D body model captures, can we compare the lesions from one time point to the other to find those that are changing, find those that are new, for example. Things that are changing is very high risk to be cancerous, so the clinician certainly wants to focus on those. But this, of course, is a very difficult problem in 3D. The difficulty is illustrated here. For example, these are two captures taken only a few seconds apart, but even still, the hand is moving in space, which creates occlusion in certain areas on his torso, for example. So in those areas, you would actually need to use the image from a different camera to look at that spot and analyze that area. So combining all of this information from all of the 2D captures is but it's a problem that we've been able to solve through our technology known as markerless tracking, which is able to take a baseline capture and a follow-up capture and map them to a common shape model with a common set of the common geometry. And so here you're seeing the arrows representing the movement in the vertices of this common shape model from the baseline to the follow-up image. We can then use this to, for example, map a particular anatomic region from baseline to follow-up. Or we can do this on a much smaller basis, a particular point on baseline, mapping it to the point on follow-up. And this is what we're using for the lesion analysis and change detection. So with the initial analysis done at each time point, we have the set of lesions found at both time points. We can then do that point mapping from baseline to follow-up and vice versa to map every pixel of every lesion that's found at one of the time points to the other one. And then we can take the difference of the images and determine which lesions have changed, perhaps which have grown, which have maybe regressed, which lesions are new, and which ones have disappeared. Sometimes lesions are excised, so we can also determine that automatically as well. Here we have a real example of a subject who is captured almost a year apart. And for this particular lesion, we can identify that it's almost doubled in area from around 6 millimeters squared to over 12 millimeters squared. So the ability to see this automatically and measure this change automatically is incredibly useful for the clinician. And to talk more about that workflow, I'll introduce my colleague Oleg.
Thank you for that, Brian. So here I'm presenting the software, and really it's the system that brings together everything from the 3D reconstruction to the AI components to the tracking components, and puts it all at the clinician's fingertips. So we have a beautiful 3D reconstruction of the body with extremely high resolution for all the moles on the body. So in order to be able to perform a comparative skin exam, you need to look at the patient side by side with what their body looked like, let's say, a year ago. So here we have the subject at 2018 and the current time point at 2019. So in order to perform a comparison, you might want to look at the same lesion at the two time points. Well, with 3D imaging, it's pretty synchronized. However, the patient's pose is going to differ because that's not something that we can control for. However, thanks to the dense correspondence that we've built using our algorithms, we can actually look at any point on the skin in correspondence. So if we want to look at the elbow, we're looking at the elbow, despite the fact that it's in two different positions in space. And if we want to go up the arm and be looking at the lesions in correspondence, you get the same continued effect. So you want to look at where's this lesion, you can zoom into it, and you're perfectly aligned onto the same lesion. So that's the first innovation that correspondence provides. The next one is typically you want to tag lesions for dermoscopy. So for example, if something looks suspicious, you can mouse over it and say, I would like to take a higher resolution microscope level image of it. However, these tags, in order for them to be global and unique, they need to live on the body. So having captured a second time point and having a correspondence, we can actually bring them across automatically. So here I'm just clicking on bring across the lesion, and you see this tiny little dot is automatically identified over here. And since we have many of them, we can actually batch process all of them and have them all brought across to the following time point. Another nice feature that we've developed is for regions where you have quite a lot of things changing, it's hard to be looking back and forth. So really what you want to do instead is to flicker the image in place. So we can look at a specific location and hit a flicker. So here you could see that this lesion, this pigmentation over here, is brand new. It was previously not there, or it was very subtle. So this is another really nice feature. So if we look at somewhere where there was a bit more change, let's look at this. You can see that previously there was a mole here and it's been excised. And you can see this flicker effect really allows you to spot the changes very quickly. So the next question is, well, once we have this great correspondence, how do we bring in the algorithms that have already found all of the lesions on the body that were presented earlier? So we do that in the lesion visualizer. So what it performs is it identifies all the lesions at each of the time points and then uses the correspondence information to actually compare the lesions and be able to detect change. So here you can see that some lesions have been identified as green. And so this is actually telling us that these lesions are new. There was previously no mark on the skin there. So if we look here, we can see that so the first square on the bottom there shows you this patch of skin at a previous time point, the next one at the current time point, and the final patch is actually showing you a difference map, where blue is an indicator of increased pigmentation. So additionally, we have yellow for lesions that are receding or decreasing in pigmentation. So this is a great automated tool which has now identified suspicious lesions which were either previously not there or have changed by a significant margin. Okay, so if we pick one, we can see in this one, at the previous time point, there seems to have been increased inflammation around this one, around this lesion, and now yellow is indicating that it has receded. And you are also able to see really precise metrics for the longest diameter, as well as color and border irregularities, which are important factors in tracking and identifying risk factors for skin. So in order to take a more in-depth look, you can actually bring up our full-featured record of the body, which, if you wanted to have everything visualized, you can, reset your filters and look at every single point on the body as visualized by these dots. However, for most purposes, we actually want something very narrow and precise with respect to things that have only changed substantially. So here you can narrow this list down to the most changed lesions, and so you can go and navigate directly to them from this interface as well. Okay, and now I'd like to hand it over to Doug Canfield to summarize the presentation.
Thank you, Oleg. That hopefully ties together a story around the value of whole body imaging and the fact that 3D stereophotogrammetry is a way of having a continuous, near complete skin surface that we can not only do analytics at a given time point to find this segmented lesion that is the ugly duckling amongst within the patient, but we can also assign anatomy areas to it, so we can track and look back at lesions that are on certain anatomical sites. And then more importantly, for us, it's about change detection, and being able to track lesions over time is a key advantage to the clinicians as they try to find the changing lesion, which is usually an indicator of risk that something is growing or changing in either direction can be an issue. And tying it all together as a complete solution. So adding the dermoscopy that you've been hearing about and tying it directly into the whole body imaging map is also a key asset to the complete solution. If you're interested in this area of research and believe that you can contribute to our team, we would love to hear from you. We are always looking for smart, hardworking, capable talent. And you can find us on our careers page on the CanfieldSci.com website. Thank you all very much.